Hey guys, this is the nuclear chemistry test review, and I want to try to make this as quickly as possible. So first things first, if you hear any yelling in the background, sorry, that's the ROTC people running in the school and doing a relay. But for now, let's head to jumping into this. So nuclear chemistry deals with the nucleus and not the electron cloud. The rest of the chemistry we'll do for the rest of the year is going to be about bonding and those all dealing how the electrons interact with other electrons from in the electron cloud of other atoms. Right now we're dealing only with the nucleus and changes that take place within the nucleus. And so since we're dealing with the nucleus, we're dealing specific with protons and neutrons, and they help determine mass, and you need to be aware of that. Mass is only protons and neutrons. And so why does that become important? Well, say I'm given an element, or I'm given a designation that an element has specifically 84 protons, does 84 protons, and let's say, and that's going to be, so that's, you automatically need to know specifically what that means. Oh, that has 84 protons, and it has 124 neutrons. You need to know what that's saying. You need to be able to tell me the couple formulas you need to write down or have a word association with that. Specifically, it's saying that I have polonium because of the 84 protons. So you need to be able to write polonium. And then you draw a dash and say, that's polonium what? Well, I have to add those two things together. So I have to add 84 and 124, and I'm going to get polonium 208. That is the mass right here. So when you see polonium 208, you know, oh, that's polonium with 84 protons and 124 neutrons. Let's do another example of one or something you might need to see. So let's say again, let's do it backwards now. Let's say I have actinium 227. And I want to figure out how many protons and how many neutrons. Automatically, I know the number of protons. The protons, without exception, is going to be 89 protons. Well, how many neutrons will I have? Remember, this is the mass. This equals mass. And it equals protons plus neutrons. So I have 89 protons. What plus 89 will get me 227? So I just simply subtract those two together, and I'm going to get 138 neutrons. That's what you do. Now, how would you write this out when we're about to do nuclear reactions? Well, you would simply say that I drop my symbol. I say AC, capital A, lowercase c, and I told you before it had 89 protons, and the proton number goes on the bottom left, and the mass number goes on the top right. The mass number goes right there. So 227, 89, actinium. That's how you would write that. Let's do the polonium example we just had. How would I write that? Well, it's polonium. I write the symbol, PO, and I write down the number of protons. Polonium had 84 protons, and the mass was 208. Mass goes left. The proton number goes on the bottom left. So mass is top left, proton number is bottom left. Now, I told you this is going to play a role when we start getting into how we draw these symbols out. Well, when we're dealing with nuclear chemistry, we're talking about nuclear radiation, and we're going to talk about the types of radiation that come from a nucleus. And the four main types are alpha, beta, gamma, and neutron. And what are the symbols for that? The symbols for alpha are 4, 2, alpha, or it can be written 4, 2, helium. The symbol for beta is going to be 0, -1, beta, or 0, -1, electron. Gamma is going to be 0, 0, gamma, and there's no other option, and neutron is 1, 0, neutron. Now, what is this telling me? Again, look at the top left and the bottom left. This right here, that means everything in alpha is going to have a mass of 4 AMU. For beta, it's going to be 0 AMU. For gamma, it's 0 AMU. And for neutron, it's 1 AMU. Charge, then, is going to be 2 protons. You see how that's 2, and protons have a +2, or a +1 charge for each one, so it's 2 +1, so that's +2. Neutron over here, electron is a -1 electron, so I have -1. That's my charge, is a -1. And you notice that both gamma and neutron both have 0 charge, so 0, 0. It's pretty easy. Because of that, other things you need to know about this is that the strength and the energy. Obviously, we can see that the alpha is the heaviest, then the neutron, and then both the beta and the gamma have little to no relative mass. Well, what does that do with energy? Well, we need to know that gamma is the highest energy, then beta, then alpha, and neutron varies depending on the substance, which means penetration strength, we're going to have gamma going through 6 inches of lead, so 6 inches of lead, with beta going through 2 inches of aluminum, and then, or being stopped by, so it can be stopped by, gamma will be stopped by 2 inches of lead, beta will be stopped by 2 inches of aluminum, and then beta will be stopped by a piece of paper. So that's what that means. Now we're going to get into a couple things dealing with radioactivity. When we're talking about radioactivity, we're going to talk about chemical reactions with these, or nuclear reactions with these, and how long these nuclear reactions will take place, or what's going to be left after that. So let's move over here to nuclear reaction equations. Let's do this first one. So I have carbon 14. Now it's telling me I have to finish out this equation. Carbon 14 is going through a beta decay, or a beta emission. How do I know that? Because it tells me specifically, and I have the symbol here. So I need to go ahead and have finish out this equation. Well, I treat it exactly like an equation. I've said many, many times. One side of it has to equal the other side. So my total mass here is 14. What plus 0 already that I have on that side will give me 14? And the answer is 14. So again, let's see how we solve this. On this side I have 14 mass, and on this side I have 0 mass. What plus 0 will get me 14? 14. And this side I have 6 protons. This side I have -1 protons. What plus -1 will get me 6? Answer is 7. Well, if I have 7 protons, now my elements change to nitrogen. Okay, we've done this one so many times. Let's do lithium. This lithium says it's going through an alpha emission, so I need to draw an alpha particle. So lithium is going through an alpha. I go ahead and put my arrow and draw alpha at 4, 2, alpha, no exceptions. Well, is everything filled out here for lithium? No, it's not. It's lithium, and it has how many protons? Well, since I know lithium has 3 protons, I'm going to put 3 right there. Now let's go look at the equation here. This side of the equation has 3 protons. This side of the equation has only 2 protons. So 2 plus what number will get me 3? Well, the answer is 1. And 7 plus what number will get 4 plus what number will get me 7? The answer to that is 3. And whatever has 1 proton, that's hydrogen. Let's review again what this is saying. This is saying that lithium, when it goes through alpha decay, so this lithium atom, this lithium nucleus, with 3 protons and 4 neutrons, is going to split off. So I have 3 protons and 4 neutrons. It's going to split off, and it's going to shoot out an alpha particle. So it's going to be 2 protons and 2 neutrons. What's going to remain is going to be 1 proton and 2 neutrons. That's what's going to remain. That's what it's saying with the emission. It's going to shoot these off and you're going to be left with something else. If you would please do the rest of these by yourself, or do a sample problem like this. Let's go do beryllium number 5, and then we'll move on to another sample problem. So beryllium goes through beta and a gamma. So I have beryllium 9 with a mass of 9, atomic number of 4, so 4 protons, going through beta and gamma. So let's go ahead and draw them. It's going through a beta, 0, -1, beta, plus a gamma, 0, 0, gamma, and it's going to be left with what? What am I going to be left with? Well, let's add everything up. On this side of the equation, I have a mass of 9, and I have 0 plus 0. 0 plus 0 plus what will give me 9? The answer is 9. Okay? Now I have 4 protons on this side, and I have -1 plus 0. So what plus -1 will get me 4? The answer is 5. Well, what does that change my element to? Well, it changes my element to boron. And again, let's keep in mind what this is saying here. It's saying I have an element here with 4 protons and 5 neutrons. And it's going to shoot off 2 particles. It's going to shoot off a 0, -1 electron, and it's going to shoot off a 0, 0 gamma. And what's going to be left? Well, what that will turn into is going to be something with 5 protons and 4 neutrons. Now, I explained it in class what happens here. Remember, what happens here is that in a beta decay, one of my neutrons turns into a proton, and it shoots off an electron right here. So that's why now I have a change in the number. I have one of these that turned into that. So remember, in a beta decay, a proton turns into a neutron. Remember, in beta decay, I apologize, a neutron turns into a proton. Let me say that right. In beta decay, a neutron turns into a proton and shoots out an electron. Do some sample problems, look for some online. I'm moving on to the next issue. Now we have half-life problems. So be good with half-life problems. Now, remember what half-life is. It's the amount of time it takes for a radioactive material to decay into a new substance. The half-life is the amount of time, let's write this out so you guys can see it, is the half-life is amount of time a substance, or one half of a substance, one half of a substance will decay. Okay? So in order to do half-life problems, you need to be aware of a couple things. When you read the question, and I might do all of these because I want to make sure that we get these done good, and if you don't need all of them, just find the ones you need help with and move on. You need to look at the question and underline the key aspects, because you're going to be asked 4 different kinds of things here. You're going to either be asked, or you need to be aware of 4 different kinds of things here. First things you're going to be asked for, you need to be recognizing the question is my substance, and I'll write this in the black so you can see this better, is my substance getting bigger or smaller? So let's get out of here. Is my substance getting bigger or smaller? And how do you know that? Well, look at the question. The question is either going to say, how much is left, or how much did you start with? Okay, so let's go look through these questions. So this says, how many remain? Okay, so that means how many remained. That said how many remains. This one said how many will remain. This one says if 5 grams of sodium-25 was removed from the reactor, how many sodium-25 were replaced in the reactor? How much were placed with, so how much you began. So this remained, how much did you start with? This one says half-life of how much will remain. Selenium-83 has a half-life of 25 minutes. How many minutes would it take? So that's a time question, not an amount question. Half-life of polonium-218 is 3 minutes. How much 2-gram sample remains? So again, remains. So you're either beginning with, you need to know if you're going to get bigger or smaller. If it says how much is left or how much remains, you're going to get smaller. So you need to figure out how much is going to remain after a period of time. If it's asking how much you begin with, your number is going to get bigger. So because it's asking how much you started with. It doesn't change the way it's going to look, though. It doesn't change what it should look like. You're still going to have the arrows going from left to right. You just that will change whether you start on the right or you start on the left. The next question that you need to be aware of is, how much is my half-life? What is my half-life? Or how many half-lives? Let me change that. How many half-lives? How many half-lives? And how do you do that? you take your total time, and divide it by half-life time. Okay, and we'll see that throughout the question. And then you need to make sure that you need to look to see if you're finding time, or determine if you're finding time or amount. Time or amount. And then finally, you make sure you show your work. Okay, let's go do some of these questions. Let's do an isotope of selenium, an isotope of cesium-137 has a half-life of 30 years. If 1 gram of cesium-137 disintegrates over a period of 90 years, how many grams of cesium-137 would remain? So step one, am I getting bigger or smaller? I'm getting smaller, so I'm going from left to right now. Now to determine how many half-lives, and the number of half-lives determine my arrows. I have a total time of 90, let's read the question. An isotope of cesium-137 has a half-life of 30 years, over a period of 90 years. That's my total time. So it's going to be 90 over 30. Over 30 years. Which is going to equal 3 half-lives. Now what this means is that I'm going to have 3 arrows. So I'm going to get smaller, so I got to find my starting amount. My starting amount is 1 gram. 1 gram of cesium. So I'll start right over here. 1.0 gram of cesium. And I go to 3 half-lives. 1 half is 30 years. A blank. I have another half-life. Is 30 years. And then I have one more half-life. Is 30. One more half-life. So let's go get smaller and see what happens. So after my first half-life, I broke down from 1 gram to 0.5 grams. After 0.5 grams, I ended up with 0.25 grams. And after my third half-life, so half of the 25 is going to be 0.125 grams. Now, did I show my work? Yes. Did I have my answer? Yes. And then in my units? Yes. So that's going to be 3 out of 3 points. Okay? So the next one. Actinium-226 has a half-life of 29 hours. 29 hours. What is it going to be asking me to do? Let's go ahead and solve this. It has a half-life of 29 hours, so that's its half-life, 29 hours. If 100 milligrams, that's what I begin with, of actinium disintegrates over a period of 58 hours, how many milligrams of actinium-226 will remain? So I'm getting smaller, and the number of half-lives is going to be my total time of 58 hours over 29 hours. That's going to equal 2 half-lives. So let's do our math. So I have 100 milligrams, make sure my units are right, 1 half-life, and then another half-life. What will remain? So 1 half-life, 1 half-life, and that's going to give me 29 hours and another 29 hours here. So that, how many total hours? Well, that's 58 hours. So 100 milligrams breaks down to 50 milligrams, and half of 50 milligrams is another 25 milligrams. That's my final answer. Let's go look at this one. This is the one where it's asking you to start from the... Now, we did this together in class, so if you go look at your work, practice this again. But this one is asking me, it's telling me I began, says, if it took sodium-225 was used in the laboratory, used in an experiment, and it took 3 minutes to get to the sodium from the reactor, from the sodium to the reactor. If 5 milligrams of sodium was removed from the reactor, how many milligrams of sodium were placed in the reaction vessel? So it's asking how many were placed. Okay, 3 minutes later if the half-life is 60 seconds. So again, it's saying how much will remain. So if 5 milligrams of sodium-25 were removed from the reactor, how many milligrams of sodium-25 were placed in the reaction vessel 3 minutes later if the half-life? So let's go through. So am I getting bigger or smaller? I'm getting smaller. How much remains? And then what's my half-life? My total time is 3 minutes. And how much is the half-life? Well, it's 60 seconds or 1 minute, and that's going to equal 3 half-lives. So let's begin with our math. I began with 5 milligrams, 5.0 milligrams, 1 half-life of 1 minute is going to give me 2.5 milligrams after another half-life. It's going to give me, that's 1 minute of course, so 2.5 is going to give me 1.25 milligrams. And then after the final half-life, so 1/2, another 1 minute, it's going to give me 1.25 divided by 2, or times 1/2. It's going to give me 0.625 equals 0.625 milligrams. Now, did I show my work? Yes. Do I have my answer? Yes. Do I have my units? Yes. 3 out of 3. Okay. Let's do number 4 because now it's asking for a time question. So the half-life of isotope X is 2 years. How many years would it take for 4 milligrams of sample to decay and to have only 0.5 milligrams? You can do this 2 ways. You can, well, let's go ahead and just work the problem out so that'll be easier for us. So let's go. This has a half-life of 2 years. So, and I have 4 milligrams. Let's see how many longer it would take. So 4 milligrams, half-life, 1/2, 2 years. That's going to get me 2 milligrams. Another half-life, 1 half-life, 2 years is going to get me 1 milligram. After another half-life of 2 years, it's going to give me 0.5 milligrams. What did it ask me to end on? 0.5 milligrams. So how many half-lives was that? That was 3 half-lives. 3 half-lives. And each is 2 years. So 3 times 2 is going to be 6 total years. Did I show my work? Yes. Do I have my answer? My number? Yes. Do I have my units? Yes. Done and done. Okay, let's do the last 2 real quick. And again, you can just go through these. You don't have to look at them all. Selenium-83 has a half-life of 25 minutes. How many minutes would it take for a 10 milligram sample to decay and have only 1.25 milligrams remain? The same kind of question, so let's go through it again. I have selenium-83 has a half-life of 25 minutes. How many minutes would it take for a 10 milligram sample to decay to have only 1.25? Let's do this then. 10 milligrams, half-life, arrow, that's going to get me 25 minutes. That's going to give me 5 milligrams. Arrow, 1/2 is another 25 minutes. It's going to give me 2.5 milligrams. Another last arrow, 1/2. It's going to get me, and again, the RTC is going to do so. I'm sorry if it's going to be a little bit, 25 minutes. And that's going to give me 1.25 milligrams. That's my final answer. That's what it wanted me to stop at. Now count that up. After 3 half-lives of 25 minutes, that's going to be a total of 50 minutes and then 75 total minutes. 75 total minutes. And you guys can do the last one by yourself. Let's go ahead on to another topic. Okay, let's go look at the people again. Remember Roentgen, he discovered X-rays. Becquerel discovered radiation. Curie discovered polonium and radium. Rutherford discovered the nucleus and alpha and beta and protons. Einstein did E equals mc squared. Oppenheimer developed or led the Manhattan Project. And Chadwick discovers the nucleus. Okay? Other things to remember. Let's go back real quick about half-lives. Another thing to remember about half-lives is that you can only go through 10 or so half-lives. Remember that from the lab. Remember, an object can only have 10 or so half-lives before it becomes too small an amount to actually measure. So remember that. So if I had something with a half-life of, that has a half-life of 20, let's call it 10 years, something with a half-life of 10 years. Okay? How many years would that be? Well, only 10 half-lives, so I'd have to, after every 10 years, so 10 times 10 times 10, that times 10 would be 100 years. So after 100 years, you would no longer be able to have a good sample of that. So example, so 10 years, so one half-life, so I'll take something that's 100 grams, let's say 1,000 grams, so 1,000 grams. One half-life, 10 years, and then that's going to be 500 grams, another half-life of 10 years, so that's 20 years, and then that's going to be 250 grams, and then another half-life, which is 30 years now, is going to be 125 grams. Another half-life, which is 40 years, so that's 10 years still, so in total of 4 years, that's going to get me, I'm going to start on the bottom here, 0.625 grams. Or 62, so 125 divided by 2 is going to be 62.5 grams. 62.5 grams. Okay? Another half-life of 10 years is going to get me 31.25. So make sure I'm right though. 62.5 divided by 2 is going to be 31.25 grams. And then another half-life of 10 years. So that's first, second, third, fourth, fifth, sixth year. It's going to give me 15 or 15.75. So it's 31.25 divided by 2. 15.625 divided by 2. There's another half-life, so it's going to give me 7.81 grams. And when you start with 1,000 grams, that isn't really, it's really not a good amount to compare it to, because after 7 half-lives, it's still a really small amount. So let's go to the 8th half-life. So this is the 8th at 10 years, so 80 years now. It's going to be divided by 2, 3.9. The 9th half-life, so 9th, it's going to be 10 years more, so we're at 90 years now. So 3.9 divided by 2, maybe 1.95. And the last one at 10, the last half-life at 10 years, my 10th half-life, is going to be 0.97 grams. 0.98 grams, really. Okay, so after 10 half-lives, starting with 1,000 grams, I have not even I have a tenth of that remaining. So that is, you can't go past more than 10 half-lives That's going to be important to note because you won't have much of a sample to compare it to. Other couple things to remember about this test: you need to be able to give me the important contributions to radiation, and how does the effects of power plant radiation have on our body. We need to know what is the most radiation, what causes the most radiation to us, and of course it's natural causes, and that's going to be radon gas. You need to know that. So radon gas, and you need to know how much power plants provide to us, how much radiation power plants do, and this is all in our notes, so go look at your notes. You need to be able to tell me how much pollution comes from power plants. Look to see if we did anything on pollution of power plants. Go look in your notes there. You need to know what the inside of a nucleus looks like. So that's it. You've got power. And disasters. You need to go over the disasters. You need to know the 3 disasters, and those are again all in our notes. So disasters, power plants and their effects, and the disasters of those power plants. Radiation coming from power plants and where most of it comes from. You need to know the different types of how power plants get their energy, and it's through nuclear fission. Nuclear fission. You need to make sure you understand what goes through nuclear fission and what's the important aspects of nuclear fission. Again, we just talked about that today, and it's also in our notes. So make sure you have that down. I think that's pretty much it. So good luck tomorrow, guys.